Hello everyone. In this video we're going to talk about principal component analysis. The prerequisites are linear algebra, vectors, inner products, projections, and in particular eigendecompositions, and also the covariance matrix. The goal is to describe principal component analysis, which is a very popular technique in data analysis. Okay, so let's go back to the example of the cities in Canada that we already talked about when we described the sample covariance matrix. So this data set has the latitude and longitude of the main cities in Canada. And the sample covariance matrix is like this. So now what we discussed when we're talking about sample covariance matrices and covariance matrices, that the covariance matrix gives you the variance of any linear combination of a random vector, and the sample covariance matrix gives you the sample variance of any linear combination of a random vector. And in particular, if you consider linear combinations that are given by unit norm vectors, you can see those inner products as giving you the variance in any possible direction of space. So for example, here we're looking at the variance or the sample variance of the positions of the cities when we only look from the southwest to the northeast, and we collapse every point onto this line. Okay, we collapse every point onto that line. We get a 1D data set like this, where we can compute the sample variance, and we saw that that sample variance can also be computed as by applying V to the left and to the right to the sample covariance matrix. If we consider arbitrary directions, then here these contour lines give the values of this quadratic function as a function of V. Okay, that circle was didn't let you see one of the V's. Okay, so this quadratic function is a function of V. When you plug in a vector V, you get the sample variance in that particular direction, and these contour lines give you the values. So on this ellipse, for example, the sample variance is 2000, here it's 1000. We're only going to consider unit norm vectors, okay, because we want the variance in a particular direction, and if we scale the vector, then that's going to scale the sample variance. And here we're just interested in the direction, not in the magnitudes of the sample of the linear combination. So then that means that we're going to restrict ourselves to, again, this red circle, and all of these values around the red circle basically give you the value of this function when V is a unit norm vector. And if you plot them in 1D around that circle, obviously it's going to be periodic, right? Because you're going round around the circle. This is what you get, okay, for different angles. And in particular, this is the value for our vector of interest that is drawn here. So now we could ask, well, this is kind of cool because it tells you the variation in every possible direction of space. And in particular, you can find the directions that have higher or lower variance. And this is interesting because that's going to tell you, like, within this d-dimensional, so here we have just 2 dimensions, right? But imagine that you had many, many dimensions. The most interesting dimensions in general are those that are capturing more variance, at least on average. If nothing is changing in a certain direction, we can essentially ignore it. And that's the logic behind principal component analysis. Let's look at this d-dimensional space of data and try to determine in what directions things are actually going on. So there's a lot of variation on average, and in what directions there's like essentially nothing going on, so we can basically ignore them. The problem now is, how do you find these directions where there is a lot of variation or not that much? Well, it turns out that we can find these directions just by taking an eigendecomposition of the sample covariance matrix. Why? Well, because of the spectral theorem for symmetric matrices. The proof of this theorem is beyond the scope of this course, but you can check it out in a book on linear algebra, or maybe you're taking our course on linear algebra and optimization. Essentially, what this theorem says is that you have a symmetric matrix and realize that by definition covariance matrices and sample covariance matrices are symmetric, then just to see that quickly, by the way, let's just do that quickly in the case of a covariance matrix. A covariance matrix is the expected value of X. I'm just assuming that things are centered because I'm being lazy. If you look at the transpose, this is the transpose of the mean, but because the mean is just taking like entry-wise expectations, this is exactly the same as transposing the matrix inside. Okay, and when we transpose an outer product, we get the transpose of this guy, which is X, and the times the transpose of this guy, which is X transpose. So this shows you that the covariance matrix is equal to its transpose. Oops, sorry. The covariance matrix. So the covariance matrix by definition and the sample covariance matrix by a similar argument are always symmetric. And if a matrix is symmetric, then it has an eigendecomposition of this form where you have, if the matrix is D by D, you have the real valued eigenvalues and you have corresponding eigenvectors that are all orthogonal to each other. And because of the fact that the eigenvalues are real and the eigenvectors are orthogonal, this, and again, you should check out any textbook on linear algebra, this means that this quadratic form that is of great interest to us, where you apply a vector to the left and to the right of the matrix, if you maximize it on that circle, so just to be clear, this is a quadratic form that is going to look essentially like the quadratic form that we derived here, okay, because this has exactly, so in the theorem, this is all of this form, so here V is equal to X, and the covariance matrix is the matrix A, okay, in the theorem, we're considering quadratic forms exactly like this, and we're also looking at this circle of radius 1 because we're considering vectors that have, well, that looks terrible. Let me try again. Let me do it in red. We're considering vectors that have L2 norm equal to 1. Okay. So what does the theorem says? The theorem says that if we're considering vectors with L2 norm equal to 1 and we're considering this quadratic form, then the maximum value of the quadratic form is the first eigenvalue and it's attained in the direction of the first eigenvector. And then if you restrict yourself to directions that are orthogonal to that first eigenvector, then that's maximized by the second eigenvector. Or if you restrict yourself again to directions that are orthogonal to the k-1 first eigenvectors, then the maximum of this quadratic form is the kth eigenvalue and it's given in the direction of the kth eigenvector. Okay, so the consequences for us are that if we want to look at the direction that maximizes the variance of random vector, okay, like the direction in the sense that you take a linear combination in that direction with a vector that has unit norm equal to 1, then the maximum is attained in the direction of the first eigenvector of the covariance matrix. Okay, so again, this like u1 to ud and then lambda 1 to lambda d are the eigenvectors and eigenvalues of the covariance matrix by this theorem that tells us that the quadratic form is maximized. The maximum of the quadratic form is the first eigenvalue, and that maximum is attained in the direction of the first eigenvector. Okay, because we're interested in a quadratic form where the matrix is equal to the covariance matrix. The maximum variance is the first eigenvalue of the covariance matrix, and this is attained in the direction of the first eigenvector. If we're orthogonal to that first eigenvector, then the maximum variance is attained in the direction of the second eigenvector, and so on and so forth. Okay, so again, if we're orthogonal to the first k minus 1 eigenvectors, the maximum variance is the kth eigenvalue, and it's attained in the direction of the kth eigenvector. If we actually compute these inner products with the direction of the ith eigenvector of the covariance matrix, these inner products are called the principal components. Okay? And the variance of those principal components, this is exactly the same as we were doing, so just to be clear, this is exactly the same as we were doing here to the data. So what we're saying is you have your random vector, okay, in this case it's d-dimensional data points, but the idea is the same, and you project it, okay, you take inner products with that particular direction, you get something like this, okay? So what the spectral theorem for symmetric matrices tells us is that if you want the maximum variance, okay, you want the scalar points with the maximum variance, then you have to use the first eigenvector of the first eigenvector of the data or the covariance matrix, if we're thinking about a random vector, in order to get the most variance, okay, of these points. And those points, okay, the points that you get when you project onto this line by taking these inner products, if you project onto an eigenvector of the covariance matrix, that's going to be called a principal component. So let me go back here. I just wanted to show you that picture. That's what we call a principal component. Okay, again, this inner product between the centered points and that vector. What is the variance of a principal component? Well, the variance of a principal component is equal to the corresponding eigenvalue. Okay, if you want to prove that, basically the variance of the ith principal component is equal to the variance of ui transpose c of x. Okay, but we know that this is just equal to ui transpose times the corresponding covariance matrix ui, and by definition of eigenvectors, because this is an eigenvector of this covariance matrix, this is exactly equal to lambda I times ui. So we end up with lambda I ui transpose ui, and we're always considering that the eigenvectors have L2 norm equal to 1, they're all normalized, so it's just equal to lambda I. Okay, that is the proof. We can also consider the covariance between these principal components that we obtain by taking the inner products with the corresponding eigenvectors. And that covariance is given by the expected value of these inner products. Realize that, by the way, the principal components have zero mean. Okay, like if you look at E of one of the principal components, this is the expected value of ui transpose times the centered random vector, which by linearity is equal to ui transpose the expected value of the centered random vector, but this is centered, so this is just equal to all zeros. Okay, so because the mean is 0, when we're considering the covariance between the two principal components, we can just take the expected value of their product. And now we can write this expected value exactly like with this trick that we used when we were deriving the variance of a linear combination. We reshuffle this so that now it's in this form. Okay, ui transpose. So this would be expected value ui transpose cx transpose uj. Okay, you should check that this is exactly the same as this. And now what we do is, because the only random thing here is this part, we put the expectation in, and what we get is again the covariance matrix. Now, because this guy is an eigenvector of the covariance matrix, that is just going to be equal to lambda j times uj. And here is where we use the fact that the eigenvectors of a symmetric matrix are orthogonal, so this inner product is just equal to 0. So what this is telling us is that when we compute the principal components of a random vector, they're uncorrelated. So they're independent, but only on average. Remember that does not mean that they're actually independent. Of course, when we're computing principal components from data, we're going to use the sample covariance matrix. But the idea is exactly the same. We're going to compute the sample covariance matrix, and then we compute the eigendecomposition, and that gives us the direction of maximal sample variance. We just saw that in the case of a random vector, we take the eigendecomposition of the covariance matrix that gives us the directions of maximum variance, and also of minimum variance if you consider the eigenvector corresponding to the smallest eigenvalue, of course. And then we can center the data and compute the principal components. Okay, for example, in the Canada data, we could compute the principal components that would give us these inner products with the direction where the locations change the most. So this is the first principal direction for the Canadian data, which kind of makes a lot of sense. It's almost west-east, but not quite. It's also tilted a little bit south, so it's west slightly north towards east slightly south. That's the direction in which things change the most, and as you can see, compared to what we had before, there's much more variance here. The second principal direction, which gives you the direction of minimum variance, because here the dimensions are only equal to 2, is this one. So essentially almost north-south. Here the variation is much, much smaller. Remember that the sample variance in the direction of a fixed vector v is computed with this quadratic form, where we apply v on the left and the right to the sample covariance matrix. By again the spectral theorem for symmetric matrices applied to the sample covariance matrix, we get that the maximum sample variance is going to be attained in the direction of the first principal direction obtained by computing the eigendecomposition of the sample covariance matrix. If we're orthogonal to that first direction, then the maximum variance is going to be the second eigenvalue, and so on and so forth, so that if we're orthogonal to the first k-1 principal directions, the maximum variance is the kth singular value, and that is attained in the direction of the kth eigenvector of the sample covariance matrix. Okay, so the sample variance that we had in this direction that we had decided upon, which was basically southwest to northeast, was 229. And that was the sample variance of all of these points that were computed by taking the inner products with that direction, with a unit norm in that direction, a unit norm vector in that direction. Okay, it's only 229. If you take the sample variance of the first principal component, it's 531, so much larger. Okay, and if you take the sample variance of the second principal component, it's much smaller, just 46.2. It's very, very concentrated. That's the direction of minimum variance, or minimum sample variance, okay, because here we're actually looking at data. Okay, so to finish, let's take a look at an example where we apply PCA to a much higher dimensional space, where we have 64 times 64 images from 40 subjects. Okay, and so basically we have 400 data points, and the dimensionality of each data point is 4096. Here we're going to treat each image as a vector containing its pixels. Okay, so this is the number of pixels. And we're going to compute PCA to find the directions of higher variance, which we're going to be able to display again as an image, because it's, these directions are vectors that have that number of pixels. So this is the center of the data, which makes sense because it kind of looks like a face. and these are the directions of this is the direction of maximum variation. Okay, so a lot of the faces have variations that have to do with the nose, the ears, and the mouth. Okay, then you can see at the directions of maximum variation. Well, some of them have eyebrows. Here we can see glasses, and so on and so forth. Okay, so this tells us that these are the directions in which we see more change within the subjects in this 4096 dimensional space. Okay, and as we go to higher and higher principal directions, here we're seeing less and less variation. Okay, so in particular, this is the direction of minimal variation, which essentially contains just like high frequency features. PCA is very useful in image analysis because, again, it uncovers these images that represent the directions of higher variance or lowest variance in this high dimensional space. Okay, so what we have learned is that principal component analysis extracts the directions of maximum and minimum variance in the data, and the way this is achieved is by taking an eigendecomposition of the covariance matrix of the data. Thank you very much.